Okay, hello everyone. This is going to be day 2 of Advent of Code. It's a little after 9 here. I don't think I'm shooting for leaderboards or anything. So we'll just, we'll take it slow and we'll work through some fun, well, hopefully fun APL ways to tackle the problem. Before we jump into day 2, I do just want to talk about a refinement that I made to my day 1 solution. This is actually what I ended up posting in the mega thread on Reddit. This solution uses recursion rather than the power operator. I am sort of, I don't know, I'm biased towards the power operator and particularly the fixed point combination that it gives you. I think it's cool. So, I see something about convergent series and I sort of go straight for it. But this is actually the cleaner solution. And this just basically, so for problem 1, if you remember from last time, we have our fuel calculation function. We apply it to our input and then we sum it, and that's sort of part 1. That's fine. And then for this one, we are recursing. Basically, we're applying our fuel calculation so we don't have to worry about the module costs. And then we have a recursion function here where the base case is, if the fuel calculation produces a value less than 0, then we just return 0. Otherwise, we are adding the fuel to the recursive call of the fuel calculation function applied against our argument. And then we just sum it. And that's part 2. So that is a cleaner way to do it. Wish I would have seen that in the recording, but I knew it as soon as I clicked stop record. I was like, oh yeah, what about recursion? It's probably simpler, but whatever. All right, cool. So on to day 2. Let's see. Int code. Oh, there's been a few of these like assembly type questions. I think, to be honest with all of you, I have not done any of these assembly type questions in APL anyway. So this might be interesting. So we have an opcode, either 1, 2, or 99. Opcode 1 adds, opcode 2 multiplies. And what does 99 do? Oh, 99 means the program is finished and should immediately halt. Okay, cool. So read the values at 10 and 20, add those values. Okay, so this is like destination 1, source 1, source 2, destination. Okay, that's cool. That's cool. Oh, interesting. And we are actually modifying, we're modifying the code in place. Alrighty. Okay, well, let's clear our workspace. And does clear workspace clear everything? No, we're still in the right directory. Okay, cool. I have downloaded the problem 2. Oh yeah, I do want to create that, but first I want to look at our problem input. Okay, so it is just like a long array of numbers, right? Okay. All right, well, as before, we are going to use inget. This will be po2.text. And we will take the first element because there's only one line. So if we just do this, we just get a big string. That's cool. And then I think what I'm going to do is I'm going to use this partition function. So yeah, if you follow this example, I can basically do something like this. So I can do not equal partition right. And if I just paste a comma here, yep. Oh, yep. And then for each, we will execute. So we get a numeric vector. Yeah, and then just for giggles, so our element 99 is way over here. How big is this thing in total? It is 149 elements long. Okay, well, that's cool. So we will assign that to P. So for Dyalog, for our solution, we'll just paste that and that'll be our first line. Actually, it's not going to be our first line because it looks like called position 0. Yeah, so this code uses 0-based indexing, which by default, Dyalog uses 1-base indexing. So, but you can change it. So you have this neat index origin function. So normally, if you do something like iota 10, you'll get the numbers 1 through 10. If you have index origin set to 0, you get the numbers from 0 through 9 instead. And then you can do things like index 0, right? It gives you 0. So it's just something that's kind of unique to APL. Okay, what's the way to tackle this? Yeah, so we have our elements, our opcodes. Now I could, well, we're updating them all in place, so I don't want to like partition this into lists of 4 or whatever. I think the best way to do this is we'll just keep an index, we'll set it to 0, and then we'll basically write a function, and this function, there's something about the power operator. Yeah, I'm just going to keep doing this. So we are basically going to execute this function until, this is slightly, until our input at index I equals 99. Okay, so what are we doing here? So basically, this is, we'll have some guards. Let me think. Let's say that we have variables A, B, C, D, and this is going to be equal to our input indexed to index plus iota 4, right? So this will take groups of 4 at a time. Yeah, and then we can say if A equals, what are the opcodes? The opcodes are 1, 2, or 99, and 1 is addition. Then we can say P at D equals B plus C, right? And otherwise, if A equals 2, there's the other opcode. I have bad memory. Yeah, if A equals 2, then we'll say that P at D equals B times C, right? And then we need to execute this on something, otherwise it won't run. So we'll just execute it on 0. And then we are going to be interested, so we'll sort of discard this result and we'll take the first element of P. Yeah, this has a reasonable chance of working. No result was expected. Oh, yeah, sure. What does this mean? Oh, this is, we're doing, wow, what is this? Oh, PD. Yeah. Okay, so if I just, no result was provided when the context expected one. So we can try and, well, first of all, Oh, yeah. We have to increase our index. All right, this is starting to get a little bit gross. Bear with me. 4. We have to do this twice because these, actually, I don't know. That is not true. I can just do it here. 4, yeah, like this. And this should not be, yeah, this should not be PD. This should be P. No, wait. Yeah, let me try this. Okay. We can debug by basically assigning this to outputs. So this is just basically like print debugging. Ooh, that's interesting. Okay, so where's our 99? Our 99 is here. Uh-huh. But we went all the way to 148. So this seems correct. $148 is our first element there. Okay. What was the result of this? Did 148 appear at the end? No? $148 couldn't possibly be our answer, could it? No result was provided when the context expected one. I think maybe, let me just try this. Yeah, all right. So this seems correct, right? Wait. Oh, geez. Let me, first of all, let's set I to 0. I think I'm getting a little bit confused here. Yeah, so we'll set I to 0. We'll set P to this thing, right? So let's just reset everything. And there it is. Right, and we're getting 148, which is apparently not the correct answer. Okay. So this all looks, this looks pretty reasonable. All the opcodes and everything looks good. Okay, let me just make sure that I'm reading this correctly. First 4 integers are at positions, yeah. Two inputs, 9 and 10, and a position of the output. Add these numbers together, then store the value at the output position. Multiplying these stored at position 0. Halting the program. Huh. Okay, so we're taking A, B, C, D. Let's get rid of this. And we're taking P which we will reset. Oh my goodness. Reset P to its former value, right? And then what are we saying? We're saying we're doing this. We're advancing the index by 4. I plus iota 4 does seem correct. Are there any example cases? We do have some example sort of test cases here, right? So, okay. Let's say that P, it's like this, right? Seems reasonable. And then we run our function here. 0 becomes 2. One plus 1 equals 2. Oh, jeez. Uh-huh, yep. Yep, so I gotta do this, right? Because we are actually, yeah, yep. So if I do this, and then I do this, oh, that's interesting. Sorry, give my brain a second to catch up here. This is actually going to be, I'm just going to index here. So we have PC. I'll do this. No, whatever. PC plus PB, right, is equal to, you're not actually adding or multiplying the numbers themselves. You are indexing the numbers that you get back into your, sorry, your result. So, and now you get 2. Now you get 2, right? Second test case. Well, let's try this one. Becomes 30, right? Right? 30. Okay. Oops. I'm feeling lucky. So if we set this to our input, and then we do this, this will give us 337061, which has, man, I was just about to say that it had a reasonable chance. Oh no, this is interesting. 99 times 99 equals 9801. Before running the program, replace position 1 with the value 12, or replace position 2 with the value 2. You know, I really got to start reading this last paragraph here. Huh. Wow. All right, let's start. Okay, replace position 1 with the value 12, position 2 with the value 2. Okay, fine. P 1, 2 is going to be assigned to 12, 2. Is that right? Place position 2 with the value 2. Yes. Okay. Right? Now, we run it. We get something Very different. Okay, anything else that I'm sort of missing here? They really, man, they kind of put these here to trick you. I just want to jump in and start coding, but. Okay, great. Part 2. Well, okay, so even before we get to part 2, let's kind of just stop and sort of take stock of things. So we can do this, and then I'm probably going to put the assignment of index 0 up here on this line. And we have this. That is quite a function. Jeez. We can probably, I think we can restructure this, but let's see what we have in part 2, because we're going to have to restructure it for this anyway. Good, the new computer seems to be working correctly. Keep it nearby. You'll probably use it again. Yeah, well, great. More assembly. Encode programs are given a list of integers. The initial state for the computer's memory. Yep. Opcodes, instruction. The values are used. Instructions parameters. 1, 2, 3, 4. This all makes sense. By the way, you'll notice that I'm reading this more carefully now this time. It's called the instruction pointer. It starts at 0. This is equivalent to sort of my variable I that I'm using. Increases by the number of values in the instruction. That's fine. I can probably build like a hash table for this, or well, sorry, this is APL. I'll build some pair of arrays or whatever. Until you add more instructions to the computer. This is always 4. Great. Determine what pair of inputs produces the output. Oh, geez. Each of the 2 input values will be between 0 and 99 inclusive. Really? All right, so it's not out of the range of possibility to just brute force this thing. Yeah, I think I'm just going to brute force it. There is probably some analysis that I can do, but this is going to be fast enough where I don't actually have to worry about it. But let's refactor things. So, this, I'm going to call this, I'm going to call this function f, and this is basically like an evaluation. We'll replace this with w because it doesn't really matter what we're applying this thing to. And well, here's what I'm going to do. This initial state, I'm going to call it s, right? And then I'm going to say that p is equal to s. So we're all happy there. Oh, I should do this. I should do this afterwards because these are just the examples for this is just for part 1, right? So we'll say this is part 1. Let's just let's just make sure we're kosher so far. Yep. Okay. Great. Cool. Now, basically, we are going to generate all the numbers from 99, 1 through 99 twice, which is fine. But so to do that, we're going to use iota here. We're going to say for 2 row 99 iota in list. Yeah, and then we'll do, can I do this? Yes. This will generate all of the inputs. So what we're going to do is we are going to say for each of these guys, we are going to basically we'll start off by saying that P is equal to S, our initial state, and then we'll say P12 is equal to W, right? And then we'll say F0 is going to return some number if this is equal to whatever this guy is, the output. Then return W, else return the empty list. And we are going to enlist this thing. This might take a while. Really? Oh yeah, because I'm giving some input now that may corrupt things. So I have to deal with edge cases now. That's unfortunate. Uh-huh. Okay, no problem. So what if this function is getting super gross, but, just bear with me for a second. So we're going to do index plus equals 4, whatever, a equals some stuff, a equals 2. This is all fine. If it falls through to the end here, we are going to return the empty list. And then we will say if alpha is equal to the empty list, or this business. And I think I have to put this in parentheses now. Right? So basically we are saying either the instruction pointer is 1, or it's 2, or it's the empty list. And if it's the empty list, yeah, that's my cat. I don't know if you can hear her or not, but she wants some attention. Sorry about that. Yeah, and then basically in P, but this won't. See now, okay, now I have to say if basically if this thing returned the empty list, right, then we have to return the empty list. Otherwise, we can return the first element of P, right? Whoo boy. And let's say, for the sake of argument, that we settle this, and then I do F0. Do I still get? I still get my part 1 answer. Okay, that's promising. That is promising. Okay. Now, what if I do this? Boolean singleton value required. Okay. Fair enough. I'm going to return 0 here. Well, no. Oh, sorry. Gosh, this is hacky. Super hacky. Well, yeah, well, whatever. Index error now. Well, all right. I mean, we just keep handling error cases. So if I is basically if I is greater than or equal to length p, then again, the empty list, we're using this for our error. Is this sufficient? Greater than or equal to, yeah, that seems okay. Okay, how about now, man? No? Oh, right. This has got to be P or plus. Well, is it 4 plus or 3 plus? Let's say 4. Dude, what is this? Oh, it's the other way around. It's the other way around. My bad, guys. 4 plus I, like this. Or, I think it's 3. Pretty sure it's 3. Dude, I got the empty list, which seems nuts because all right, let's just slow down. Um, You know, hang on a second. Maybe I don't have to do any of this. Right? Maybe I don't have to care. Because in Dyalog, there's this fun thing called error guards. I've only used this once, but let me try it. Dyalog error guards. So what an error guard does, this error guard will catch. Okay. Let's check this out. Basically, okay, let's go back and say, where was our function before? Remember the old days when our function was nice and simple and it just looked like this? Those are the good old days, man. What if I told you what if I told you that we could guard it? Right, so we do F0, assign it to like A. And we say, if there's any sort of error, we just return Zilda. It's basically like try catch. Otherwise, we return A. Domain error. But I mean, I want the result of that execution. That's the thing. If I don't do this assignment, will the error guard catch it? Apparently not, which is sort of annoying. In the presence of an error guard is to isolate it with an inner function. Guards. Oh, no, I saw it. Error guards. I don't think this is going to be any more helpful, though. Oh, here we go. Can I change this? I thought I was looking at the version 17.1 help. Oh, well, okay, whatever. Error guards. Trap domain and length errors. Oh, I'm using this incorrectly. So this is like 0, A assign F0. Like this. I think. No. To be evaluated as the result of the function. Huh. 2 add 3. I see. Okay, so we can just do 0 like this maybe. Still get the empty list though, which is sort of annoying. So if I do our original 12.2, yeah, this doesn't work. I'm not setting this globally. This always trips me up. Like this. Okay, getting closer though. I think also we need to set this to 0 globally. Oh, yep. And then there's several answers. Quite a few answers actually. Oh yeah, no. Well, sure. So now I need to do this equals, then return W, else we return the empty list. Like this. 4259. Oh, what is 100 times noun plus verb? Sure. 100 times, it is apparently 10/100. Ah, geez. Oh, this is 100 times noun plus verb. So 100 times 59 plus, like this. You work with APL, order of operations starts to decay somewhat. Yeah, this would be 100. This would be 1200 plus 2. Yeah. 4259. I have 5 seconds left to wait. Oh my gosh. The suspense is killing me. By the way, I did get noun and verb right, I think. Talks about nouns and verbs. Where was that? Noun. Oh my gosh. Value, place, and address one is called the noun and verb. Yeah. Okay, 4259. Hey! Alright. Great. And it only took me like a million years. That's fine. Now, we have some cleaning up to do, for sure. So this is sort of what we've got as of now. This is, this is a bit gross, if I may say so myself. Let's see if we can clean this up somewhat. So let's start with our function up here. This, I think we could do, basically we're doing b plus c. I think we can simplify this with, basically what if we were doing like, let me just copy this line. We'll put it down here. What if instead of these conditionals, we had something like B, and we'll do a train with C, and we'll do plus, comma, multiply. We'll index this thing by a minus 1. Sorry, a minus 1. That's right. And we don't have to worry about indexers because we're catching all that stuff. And then we'll just say PD gets this. Dude, how on earth did this work without global assignment? Well, whatever. Okay, this is nicer. I think this works. So if I do this, I should still get part 1, part 2, 148. Ooh. 148 is not the correct answer for part 1. Right? Your puzzle answer was 586 whatever. So we're indexing. This does do what I think it does, right? So if I do like 12, 24, plus, comma, times. Yeah, that's right. And then if I want to index into it like, 0th or the 1, this is sort of what I'm getting at. Yeah. What is going on here? Why doesn't this work? Is it really because that can't possibly be it. Right? There's no way. There's no way, man. No. Oh, yeah, duh. My apologies. We do still have to index this. For some reason, I keep getting caught up on this. Yeah. All right. This is a bit simpler. And then Yeah, we do not have to care about the index errors. That's what we learned today. Okay. By the way, just to get part 2 sort of mechanized, let's say, we have our function g here, right? This is going to be a little bit cleaner, and we're going to do, for each one of those, we're going to do g, and then we're going to do, what was it, 101 times like this. 4259, as far as I know, is our answer. Yeah. Okay. 99 equals IP. Dude, on it, this looks pretty good. Pardon me. This looks pretty good. Now, here's something interesting. If I'm not actually doing, let's see, so here I'm doing assignments. Yeah, honestly, I'm inclined to ship this thing. No, I'll tell you what. Here's what we'll do. We'll lift this P12 nonsense out. This is probably the last improvement that I'm going to do. Put it here. Like this. And yeah, and then we can do F12.2, right? So let's just say that we go with this. Does this work? Oh, it does. Here's the fun part. So if I do F4259, oh, I get an index error. Well, I guess that's to be expected. But I will lift this as well and put it here. Geez, and this too. Actually, all this stuff should be there. I think this is okay as a local. Huh. Yeah. Uh-huh. I might just shake this out a little bit. Yep. We no longer need this. Ooh. It's a new one. You don't get anything back from this anymore. What if we do global assigns here? Let's get rid of this. And here we're going to do FW. Maybe something like this. Very nice. So, I mean, this function here is just sort of... Okay, let's get crazy. What if I just take these out entirely? Well, I mean, let's comment them out. Oh, jeez. We'll comment these out. I'm just going to set these locally. Like this. That actually works. All right, cool. So we don't have any global variables. We just set them all in this function here. I think that's enough simplification for right now. So this is going to be the solution. Yeah. Hopefully this was, I mean, this is kind of, this problem, I don't know if this problem is super well suited to APL. Well, maybe it is. Someone's going to come up with a very clever solution, I'm sure. But yeah, thanks for watching, and hopefully you learned something. Thanks.